Hello, today we're continuing our series on particle physics, this time looking at rotation and then the SU3, SU2 and U1 matrices or operators. I should just say that in this series, at this point, I would have prepared videos on the Standard Model and then quantum electrodynamics and quantum chromodynamics. But in fact, I've already prepared those videos. They are already in the particle physics playlist. So if you want to see a logical sequence at this point, if you haven't already done so, you should look at the videos, the links to which are on the screen. But assuming that you've done that, then let me just remind you that at the end of the last video in this series, we showed that the commutator of the angular momentum in the x direction with that in the y direction was equal to I h bar Lz, and that the commutator of the spin in the x direction with that in the y direction was equal to I h bar Sz. And we also showed that you could produce similar commutators of y with z and z with x, and in each case the one that doesn't appear in the commutator is the one that does appear on the right hand side. And essentially a key point of what this means is that you cannot measure the angular momentum along the x and the y coordinates at the same time because the commutator does not equal 0. All of this comes out of the material that we developed in quantum mechanics concepts. And similarly, you can't measure spin along 2 axes, or indeed 3 axes, at the same time. You can only ever measure angular momentum and spin along one axis. Now I pause at this point just to point out that we are talking about angular momentum and spin, and of course we can very easily fall into a trap here of saying, yes, we know what angular momentum is, that's kind of when the Earth goes around the Sun, that's got angular momentum. We know what spin is, the Earth spins on its own axis, so that gives us a picture of spin. But we're talking quantum mechanics here, so we need to be very careful that these analogies with the classical world, or the real world that we inhabit, only take us so far. And we have to recognise that angular momentum and spin, when applied to quantum particles, are different to what we observe in the real world. So let's think about some particles and what's called the spin states. There is a spin equals 0 particle. That's, for example, the Higgs boson is a spin 0. That means there is only one spin state. It can't move from any state to any other because there is only one possible state for it to be in. Then there are the fermions, like electrons and quarks. And that is called the S equals 1/2 state. And what that means is that the spin can be either half h bar or minus a half h bar. There are two possible states. We have labelled this up and this down. So when you measure spin, you only ever get one of two results. You either measure up or down. They are officially half h bar and minus half h bar. Why? Because the difference between the two is h bar, and we showed in quantum mechanics concepts that angular momentum and spin do not come in continuously variable amounts. They always increase by a quantized amount of h bar. So if you want to change from one angular momentum or spin state to another, you have to do it in units of h bar. It's quantized. So when spin changes, it moves in units of h bar from minus a half to plus a half, or from plus a half to minus a half. And those are the only two options for fermions. But bosons, like for example photons, they have 3 states: plus 1 h bar, 0, and minus 1 h bar. And that's called the spin 1 state. And you'll notice that once again, the states are h bar apart. And then I'll just show you another state, which is the S equals 3/2 state. This is for composite particles that we'll meet a bit later on. And here we've got a possible 3 over 2 h bar, half h bar, minus a half h bar, and minus 3 halves h bar. And once again, you'll notice that each of those are h bar apart, but there are now 4 states. And you will also to notice that the number of states is given by the value of s, 2 times the value of s plus 1. So in this case, s is 0, so 2s plus 1 is 1, there's 1 state. Here, the value of s is a half, 2s is 1 plus 1 is 2, there's 2 states. Here, 2s plus 1 is 3, there's 3 states. Here, 2s is 3 plus 1 is 4, there's 4 states. So this formula gives you the value of the number of states depending on the value of s, which you'll notice in each case is the maximum value of the spin states. So suppose I now bring 2 electrons together. Remember, electrons are fermions, they are spin 1/2 state. So if you bring 2 electrons together, there are 4 possible configurations. The 2 electrons can both be spin up, or they can both be spin down, or one can be up and the other down, or one can be down and the other up. Those are the only possible combinations. And if they are spin 1/2 and up is plus half, down is minus a half, then this is plus half, that's plus 1, total spin. This is minus a half is minus 1, total spin. This is plus a half is 0, total spin. And this is minus a half plus a half, 0, total spin. So a pair of electrons have these possible spin values. And if you go back to the previous diagram I drew, you'll see that plus 1, 0 and minus 1 are the spin states of a boson, like a photon. So in essence, when you bring 2 electrons together, you create the equivalent of a boson state. But you'll notice there are 4 possible states here, and I said that the photon boson spin 1 state only had 3 possible values. And what you've actually got here are the 3 spin 1 states, and you've also got 1 spin 0 state. These 2 are clearly the spin 1 states. It's not as simple as you might imagine. It's not as simple as saying that one's the 3rd spin 1 state and that's the spin 0 state. We are talking here quantum mechanics, so quantum mechanics states you have superpositions, so there will be a superposition of those 2 states that form the 3rd of the S1 state, and another superposition of these 2 states form the spin 0 state. So the 4 states you get with electron pairs actually make up 3 spin 1 and 1 spin 0 state. What about quarks, which are also fermions? Well, from the video which you should now have watched on the standard model, you'll see that we can have quarks arranged in a way that is familiar. 2 ups and a down is a proton, and an up and 2 downs is a neutron. So quarks can be arranged in this form, and that produces the 2 most basic particles, which of course are not now fundamental particles. We now know that protons and neutrons are not fundamental. They each contain 3 quarks, and the orientation of those quarks, or rather the nature of those quarks, whether they're up or down, determines protons and neutrons. Now, a neutron that is on its own, a single neutron, not one that is in the nucleus of an atom, but a free neutron, will only last for about 10-20 minutes before it decays into a proton. And the way that it does that, you'll see, is that it simply takes the down proton in the neutron and converts it into an up quark. Sorry, did I say that's a down quark in the neutron becomes an up quark, and that changes the neutron to a proton. Or in the sun, it's the other way round. In the sun, a proton is converted into a neutron, so that 2 protons and 2 neutrons can fuse together to form helium. That's all that goes on in the Sun. The Sun is just full of protons. It's hydrogen, basically. The electrons are, of course, stripped off because there's so much energy that the atoms are ionized. Ionized hydrogen is simply a proton. And then in the Sun, you've got this process whereby one of the up quarks in a proton is changed into a down quark, thus forming a neutron. And then you take 2 protons, 2 neutrons, and fuse them to produce helium and energy. And that's what the Sun does for 10 billion years. We'll see why it takes 10 billion years in just a little while. But these are not the only configurations of quarks. You could indeed have 3 up quarks. And if you did, then that of course would have a combined spin of 3 halves, because we know that quarks each have a spin of a half. So 3 in the up direction would give you a 3 halves spin particle. But that is not a proton, nor is it a neutron, because the orientation for protons and neutrons is different. There is such a particle that has 3 ups, but it doesn't survive very long. What happens, and we can draw a Feynman diagram here, and if you're not sure about Feynman diagrams, I have a video on Feynman diagrams, and hopefully the link is being shown on the screen now. But let me just draw the Feynman diagram for what happens if you have a particle that starts, which is essentially up, up, up. So there, Feynman diagrams in my case are going to go, time is going to go upwards, so we're going to see what becomes of it as it goes upwards. And what happens is that the ups go like this. So we've got up, up, up. But we also produce a down-anti-down pair. Remember that a particle-antiparticle pair can emerge out of nothing. This is a down, this is an anti-down. So you can always, in quantum fluctuations, you can always create particle-antiparticle out of nothing. Well, we recognise this beast. That's an up-up-down. That's just a proton. That will continue forever. An up anti-down is a pion, or a pi plus. But a pion itself won't last very long. It's a meson, and mesons generally don't last very long because, of course, they are comprised of a particle and an antiparticle. So they're not going to survive for very long. And what happens is that the pion quickly decays into a muon, or in this case a muon plus, that's an anti-muon, plus a mu neutrino. From the Standard Model, you'll recall that the muon is in the electron family. The electron has 3 types, an electron, a muon and a tau. The muon and the tau are just heavy versions of electrons. They don't survive very long. They decay to their basic form. So the muon itself will then decay to a positron, that is the antimatter version of the electron, plus an electron neutrino. And of course, in the event that you're not in a pure vacuum, the positron will very soon find an ordinary electron and annihilate. So unless you're in a vacuum, that positron will soon annihilate with an electron and produce a photon which carries the energy away. So if you start with a particle that's an up, 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 it will quickly decay into a proton, which will remain a proton forever, and a pion, but the pion itself decays into an anti-muon, and that will quickly decay into a positron, and if you're not careful, that will find another electron, annihilate and form a photon carrying the energy away, leaving just the mu neutrino and the electron neutrino. But here's a problem that we covered in the video on quantum chromodynamics. Let's take, for example, a proton, 2 ups and a down. Pauli's exclusion principle says that you cannot have 2 fundamental particles in the same quantum state. That, for example, is the reason that electrons occupy different energy levels in atoms, because electrons cannot occupy the same quantum state. And yet, on the face of it, it appears that in this nucleus of a proton, or within the proton, you've got two up quarks, which on the face of it are in the same state. Now, that either means that Pauli's exclusion principle is wrong, which turns out not to be the case, or that there is something that we don't yet know about that distinguishes this up quark from this up quark. And what has happened is that people have labelled that another quantum state, and they call it the colour state, from which we get quantum chromodynamics. So what they say is there is something that distinguishes this up quark from this up quark, and we will call that a colour. Of course, it's got nothing to do with colour. There's no question of quarks being coloured. This is just a label. So we call one of them a red quark, one a green, and one a blue. And there are three different colours in every three quark combinations. And the point about that is that whatever it is, whatever that quality is, that quantum quality, it distinguishes these two up quarks. One of them's a red and one of them is a green. So if we go back to the standard model, where you'll recall that in terms of quarks we showed that there was an up quark and a down quark, a charm quark and a strange quark, and a top quark and a bottom quark, what we're now saying is that each of those can have a different colour. Or in other words, they have a quantum state that varies depending on whether we assign a red, a green or a blue. The charges on those quarks, if you remember, the up quark has 2/3, the down quark has -1/3. And then the charm and strange and the top and bottom are just heavier versions of the up-down combination. So they too have the same charges, 2/3, -1/3, 2/3, -1/3. And the difference in charge between these two is +1. 2/3 minus -1/3 is +1. Now we can also add in this format the electrons in the standard model. So for example, the basic form of electrons are, or leptons rather, are the electron, neutrino and the ordinary electron, where the charge is 0 and -1. So once again, the difference between these two charges is +1, just as the difference in the charges of the quarks was +1. And then you've got two more heavier versions of this couple. There is the mu neutrino and the muon, and the tau neutrino and the tau. Those are just heavier versions from the standard model of the electron neutrino and electron pair. And they too have similar charges, 0 and -1, 0 and -1. So essentially, as you go along this bit of the table, what you've got are pairs where the difference in charge in each case is 1 whole unit of charge. And what we discover is that nature is essentially flipping these states. When you're changing a proton to a neutron, that is done by flipping between up and down quarks. We shall see that the strong interaction, and this is what I showed in the quantum chromodynamics video, the strong interaction is achieved by flipping between red, green and blue quarks. This interaction, flipping between up and down, is the weak interaction, the weak nuclear force. So we've got a weak nuclear force that exchanges these, and we've got a strong nuclear force that essentially exchanges these. And just a reminder, how does the strong nuclear force change the colours? Well, the way it works is, let's suppose we've got a red quark. So here we are, a red quark. This is a Feynman diagram. The red quark remains red. But at some point we can have a blue-anti-blue combination appearing out of nothing. This is the blue, this is the anti-blue. And what you've therefore got is a red quark becomes a blue quark with a red anti-blue gluon being emitted. And it's that gluon that is responsible for holding the nucleus together. So this is the pattern. You can change a red to a blue by the emission of a red anti-blue gluon. If we use the same kind of analogy, we can say that this is the same sort of thing that's happening as far as ups and downs are concerned. Let's start with a down quark, which remains a down quark. But let's produce an up-anti-up combination of quarks. So this now becomes the up, and this is an anti-up. So now we've got, just as we had a red converts into a blue by the emission of a red anti-blue gluon, now we've got a down changing to an up by the emission of something which has a kind of down anti-up nature, and we call that the W minus. So this beast here is a gluon, this here is a W minus, and they are both known as bosons, or in some cases gauge bosons. They have the nature of what's called exchange particles. They are the things that enable this exchange to take place. So this is the mechanism for the strong force, which is the colour change, and this is the mechanism for the weak force, where downs change to ups and ups change to downs. So what we just showed was that a down can become an up by the emission of a gauge boson, which we call a W minus, and that W minus has the characteristic of a down anti-up, because essentially it is taking the down and converting it into the up, and therefore it must have this nature to balance the equation. It also carries away a single negative charge, because we're changing from a minus 1/3 charge to a plus 2/3 charge, and the way you do that is to carry away a minus 1 charge. But it must also be the case, if you remember the diagram we showed that downs and ups have a charge difference of +1. We also showed that neutrinos and electrons have a charge difference of 1. So you could have the same situation, that you have an electron becoming, as it were, a neutrino, also by the emission of a W minus. I showed in the model on Feynman diagrams, I made the statement that anything that can happen does happen, and also that you can always reorder the Feynman diagrams. So for example, in this case, I could simply take this electron neutrino which is going out and say that is equivalent to an anti-electron neutrino coming in. So that's perfectly possible. Or I could redraw this diagram the other way round. I could have a W minus coming in and becoming an anti-electron neutrino and an electron. All right, it works both ways. You can have an anti-electron neutrino and electron which become a W minus, or you can have a W minus that becomes an anti-electron neutrino and an electron. All things are possible. So if we take that combination and put them all together, what we can say is have a down becoming an up by the emission of a W minus, but that W minus can also then become an electron and an anti-electron neutrino. And that is precisely what happens when a free neutron converts into a proton. Because what you've got is another two quarks here which don't change. So you'll have a down and an up, which stay up and down. But this is an up, down, down. So this is a neutron. And this is an up, down, up. So this is a proton. So you've got a neutron converting to a proton. Two of the quarks don't change. The down quark of the neutron changes into the up quark of the proton by the emission of a W minus. And that W minus then decays into an electron and an anti-electron neutrino. Why does it do that? Well, it just so happens that the W minus is 80 times heavier than the mass of the neutron, or indeed the mass of the proton. How can a neutron produce a particle that's 80 times heavier? Remember, E equals mc squared. Energy is related to mass. So if we've got 80 times the mass, we've got 80 times the energy. How can that happen? Well, the answer is that we invoke the essential bits of Heisenberg's uncertainty principle, which is usually written that the uncertainty in momentum times the uncertainty in position is greater or equal to h bar over 2. That's the standard form of Heisenberg's uncertainty principle. We developed that in quantum mechanics concepts. But there is another version of that principle that says that delta E delta T is less than h bar. And what we're saying is that you can have an uncertainty in energy over an uncertainty in time as long as it's less than h bar. In other words, out of nothing, you can, as it were, borrow energy, but the more energy you borrow, the less time you can borrow it for, and the deal is you have to pay it back. So you can create a W minus, which is a massive particle, so it's high energy, in the sense that it's high mass. But since it's high energy, you can only borrow it for a very short time. So that W minus can only exist for a very short time before it has to pay back that energy to the vacuum from whence it came, and then it decays into an electron and a neutrino. And that's fine, because the masses of these two, of course, are nothing like the mass of the neutron, and the excess energy can go into kinetic energy of those particles. In the Sun, precisely the same thing happens, except it's the other way round. Now we have an up quark changing into a down quark by the emission of a W plus boson, because it's now carrying away a positive charge. And that will then decay into a positron and an electron neutrino. And of course what you've got here, just before, as we had before, two other quarks which don't change. So there'll be a down quark and an up quark, which remain down and up. So you've got an up, down, up, that's a proton. And here you've got an up, down, down, that's a neutron. So in the Sun, a proton converts to a neutron by the emission of a W plus boson, which then degenerates into a positron and an electron neutrino. The positron will then meet up with all of those electrons in the Sun which have been stripped off the hydrogen atoms and annihilate and produce yet more photons and energy. And the electron neutrinos stream out of the Sun by the billion, but neutrinos hardly ever interact with anything. So those neutrinos are passing through the Earth. Indeed, they're passing through you at a massive rate, but you have no way of knowing it because they don't interact with you, so they just pass through and come out the other side and go on their way. Now earlier we referred to a pion, specifically the pi plus, which is a meson and has the nature of an up quark and an anti-down quark, but that of course is equivalent to a W plus, which has the same nature of an up quark and an anti-down. because what the W is doing is taking an up and producing a down. So in other words, it has to take the up away and give you a down in a down-anti-down pair. So what this means is this gives us a hint of how a pion can decay. If you like, a pion, which is the equivalent of a W plus in the sense of its nature of quark structure, can then decay into, well, it can decay into a positron and an electron neutrino, but it could also, of course, decay into a heavier version of the electron, the anti-muon and a mu neutrino, or the anti-tau and a tau neutrino. And there will be probability amplitudes, as we learned in quantum mechanics concepts, for each of these decays. And when you're talking about a pion decay, the highest probability amplitude is this one, which is why in the earlier diagram I showed that the pion decays quickly into an anti-muon. But of course an anti-muon then will decay into its smaller version, less heavy version, lighter version of the anti-electron or positron. So now just a very quick review. I'll redraw the diagram that I drew before. We said that in the standard model you have quark pairs, up, down, charm, strange, top, bottom. Each of those can have red, green and blue. And we have said that the exchange between red, green and blue is the mechanism for which you get the strong nuclear force, and the exchange between up and down, or indeed charm, strange or top, bottom, is the mechanism by which we get the weak nuclear force. So a flipping between two states is the weak nuclear force, a flipping between three states is the strong nuclear force. Now we need the maths. And the maths we're going to use is the mathematics of rotation. In a sense, it's the rotation between these states that is going to be achieved in what follows. So first, let's just think about what we mean by rotation. Here is a set of coordinates, x, y, and z. And here is my vector of length r. And in polar coordinates, we will say that that will have the polar coordinates r, theta, and phi, where theta and phi represent the angle of r against the xy plane and against the z axis. Now, if I rotate that vector, one thing that won't change is its length. If you rotate it, it stays the same length, it just points in another direction. But of course the two angles will change and become theta prime and phi prime. And in quantum mechanics concepts, specifically in the third video that I produced, we showed that there are various what we call spin states, which represent the axis of the spin, which we call psi. And for example, the up state we said was 1, 0. The down state was 0, 1. And more generally, we could represent the spin state as alpha, beta, where alpha, this is all quantum mechanics concepts, alpha is the probability amplitude of the spin being up, beta is the probability amplitude of the spin being down, and the total probability of it being up is alpha, alpha star, because to get the total probability you have to take the probability amplitude and multiply it by its complex conjugate. And the probability of measuring down is beta, beta star. That is the probability amplitude of down multiplied by its complex conjugate. And since when you measure the spin against any axis, you can only get one of two results, up or down, that means that the total probability of up plus probability of down must equal 1. And so alpha, alpha star plus beta, beta star equals 1. All of that is explained in much more detail in Quantum Mechanics Concepts Part 3. So let's take a quantum state representing the spin of, say, an electron, alpha, beta, which of course we could also have represented with our Dirac notation as A and rotate it so that it now produces alpha prime, beta prime, which we can call A prime. And basically what we're saying is we take a spin state like this and we rotate it so it now looks like this. This is only 2 dimensions, obviously there are 3 dimensions that we can rotate. And what you can say is that the probability of this being measuring, giving you an up, is much higher than the probability of this state giving you an up. So the probability amplitudes change when you rotate the vector. And now I'm going to go through precisely the same maths that I used in Quantum Mechanics Concepts Part 6. In that I took a vector state, let's say this is a spin state, alpha beta, and I allowed it to emerge over time. And from that we developed the Schrödinger equation. But on this occasion, instead of going over time, what we're going to do is we're going to rotate. So we're going to rotate A using an operator. Everything you do to a state, you do via an operator. We've learnt that of old. So we're going to use a rotation operator acting on A to produce a new state, A prime. Similarly, if we have a state B and we operate on it with the rotation operator R, that will act on B to produce a new state, B prime. Or I could take the bra vector of B, and of course I can rotate that. That will be B, R, Hermitian conjugate. Remember, B is the complex conjugate, the bra vector of B is the complex conjugate of the ket vector B. But when you do a complex conjugate of an operator, you take the Hermitian conjugate, which is essentially the transposed complex conjugate of the operator. And that is going to produce, of course, a bra vector state of B prime. Now let's ask what happens if you take the inner product of B with A. And that is essentially rotated. So you're going to get the rotated version of the bra vector of B, which is simply B R dagger, times the rotated version of the vector A, which is R A, from here. And now we use the same logic we used before, which is that whilst A and B may change when you rotate them, the inner product between them does not, because this inner product is just a number. So you can rotate B and A by the same rotation operator, but the inner product won't change. So BA doesn't become this term, it actually equals this term, because there is no change between them. Make that clear. They are equal. And the only way they can be equal is if this term is the identity operator. Because remember, the identity operator acting on A simply gives you A. I is the matrix equivalent of the number 1. If you multiply I by a vector, you just get the vector that you started with. And this means that the rotation operator, or rather R dagger times R, is equal to the identity operator I. And we showed in quantum mechanics concepts that when that happens, this rotation operator has a special name. It's called a unitary operator. Okay, so let's take that unitary operator, which is the rotation operator, act it on state A and produce state A prime. So far so good. But if I take the operator and act it on state A, but I rotate it through an angle of 0, which essentially means, of course, I don't rotate it at all, then the vector won't change. If I don't rotate it through any angle, there is no change. And therefore, in those circumstances where the rotation angle is 0, R simply equals the identity operator. because the identity operator acting on A gives you A. So when you don't rotate it at all, the rotation operator becomes the identity operator. Well, now I want to know what happens if I rotate it through a very, very tiny angle. So now we're just going to do an absolutely eeny-weeny rotation. Well, that's going to be the equivalent of I, which is what it would be if you didn't rotate it at all, plus a little bit. And remember from Quantum Mechanics Concepts Part 6, we showed how you write a little bit. It's I, epsilon, and then another operator, all acting on A. Epsilon is a very, very, very small number. That's essentially the little bit of difference between what you would get if you don't rotate at all. This bit is you don't rotate at all plus a tiny, tiny rotation. Well, this of course simply means that R, the rotation operator R, is equal to I plus I epsilon m, right? Because that's R is essentially that. And I can also write what R dagger is. That's going to be I dagger, but the complex conjugate, or the transpose complex conjugate of an identity operator is simply the identity operator. You know, in a 2x2 operator, the identity operator would be just ones along the diagonal and zeros everywhere else. And if you look at if you transpose that and complex conjugate it, you get the same thing. So the Hermitian operator, the Hermitian conjugate of I is just I. And then minus, because we're doing the Hermitian conjugate, I epsilon m dagger. So now we've got the values of R and R dagger. But we recall that these are unitary matrices, and R dagger equals I. We now know that R dagger equals I. That's the condition of being a unitary matrix. So let's do it. R is I plus I epsilon m, where I and m of course are operators, and we're multiplying that by R dagger, which is I minus I epsilon m dagger, and that we say is going to equal I. These should have hats on. The identity matrix I. Multiply that out. I times I is I squared. Well, I squared, of course, is simply I, because I is the matrix equivalent of 1. 1 squared is 1. Then if we multiply these two terms, we're going to get plus I epsilon into m minus m dagger. And then we've got to multiply these two terms, which is going to give us minus I squared epsilon squared m dagger. And that is all going to equal the identity operator I from here. Now epsilon is a very, very, very small number. So epsilon squared is so minuscule that it becomes completely irrelevant. So that term you can now forget. And now we've got that I plus something equals I. So that plus something must equal 0, because I equals I, that has no effect. Well, I and epsilon don't equal 0, so that means that this term here must equal 0, which means that m equals m dagger. And that is the condition for a Hermitian matrix, which we've learned before. That makes it an observable or a measurable. Now we've said that R, the rotation operator, is a unitary matrix, which means that R dagger equals 1. There is a thing called a special unitary matrix, and the special unitary matrix has a determinant of 1. I'll explain what I mean. If the matrix is, I'll just do a 2x2 matrix, if the matrix is given by A, B, C, D, then the determinant, which we show by putting straight lines on either side, is equal to A, B, C, D in straight lines. That means determinant. And its value is AD minus BC. That is to say, it is the product of the diagonal minus the product of the off diagonal. It's a bit more complicated if it's a 3 by 3, but let's just stick with 2 by 2 at the moment. And what we're saying is that for a special unitary matrix, the determinant of M equals 1. So AD minus BC equals 1 is a special unitary matrix. There is also a thing called a trace of the matrix. And the trace of the matrix is simply given by the sum of the diagonal, A plus D. And for a special unitary matrix, that equals 0. So if you have a unitary matrix whose determinant is 1 and whose trace is 0, that is called a special unitary matrix. And special unitary matrices are going to prove to be very important as rotation operators for both getting between red, green and blue, and between up and down in terms of our quarks. Why? Because it works. That's the maths that accords very much with the experimental results. Now it turns out that we have already met special unitary matrices. I'll write them up for you. 0, 1, 1, 0, 0, I, minus I, 0, and 1, 0, 0, minus 1. If they don't immediately spring to mind, I'll remind you that they were the spin operators, sigma x, sigma y, and sigma z. The matrices you use to measure spin of, say, an electron along the x, the y, and the z axes. And they were called Pauli matrices. But let's just think about what the determinant is. The determinant, I said, should be plus 1. Actually, in some cases, it will turn out to be minus 1. Doesn't matter whether it's plus or minus 1. The determinant here will be 0 times 0 minus 1 times 1. That's minus 1. The determinant here is 0 times 0 minus I times minus I. That's plus 1. The determinant here is 1 times minus 1 minus 0 times 0, which is minus 1. So the determinants of these matrices are 1 or minus 1, so that's okay. The trace, 0 plus 0 is 0, 0 plus 0 is 0, 1 minus 1 is 0. So we've got 3 matrices, which are 2 by 2, which have determinants 1 or minus 1, and a trace equal to 0. So these Pauli matrices that we have used in the past for measuring spin are also special unitary matrices, and we will use those for a different purpose now. These are the matrices that are going to be responsible for converting between up and down quarks. This is the maths that we're going to achieve, and it's done by virtue of a special unitary matrix, and that special unitary matrix is a 2 by 2 matrix, and so we give it the value 2. So these are SU2 matrices, and they are the mathematics which enable us to do the weak nuclear force which exchanges up quarks for down quarks. Well, if you need a SU2 matrix in order to move between 2 states, up and down, I wonder what you will need to move between 3 states, red, green and blue. And of course you've got it. You will need a special unitary matrix which is 3-dimensional. And this means that we're going to have matrices, because there are in fact 8 of them. We won't worry about what they are just at the moment, but there's a 3 by 3 matrix that will operate on a 3-dimensional vector. And what will that 3-dimensional vector essentially represent? It will be the probability amplitude for red, the probability amplitude for blue, and the probability amplitude for green. And what that matrix will do is to change the values. So you will get the prime values of red, blue and green. So essentially what we're doing is we're taking the probability amplitudes and rotating them so that you are shifting between reds and blues and greens. And that's the SU3 operator, and that is responsible for the strong nuclear force. So, redraw this diagram again: up, down, charm, strange, top, bottom, red, green and blue. It's the SU3 that is responsible for the strong nuclear force, which changes the colour, and it's the SU2 which is responsible for the weak nuclear force, which essentially changes ups to downs, protons to neutrons. So our standard model will consist of SU3, which is the strong force, the change of colour, and then you also need the SU2, which is the weak force, moving from up and down. But we also need to remember that there's something else going on in the nucleus, which is, of course, something going on at fundamental level, which is the Coulomb force, the electromagnetic force, or the quantum electrodynamic force, QED. That is mediated by photons, photon exchange. Photons do not change colour, they do not have colours. They do not have ups or downs. So they don't need special unitary matrices. They only have one state, and you can represent that by the U1 matrix. And this is essentially the quantum electrodynamic, or if you like, just the Coulomb force, the fact that there are charges associated with fundamental particles. And so that's why, if you've ever seen this formulation written in books, the standard model is an SU3 cross SU2 cross U1, and you've ever wondered what on earth does that mean, that's essentially it. You need some form of mathematics which is based on the 3x3 operators that will shift red to green to blue, thus essentially achieving the strong nuclear force. You need a 2x2 operator, SU2, which will shift ups to downs, thus achieving the weak force, and you need something that represents the Coulomb force, and that is essentially the basis of the standard model. Hello, today we're continuing our series on particle physics, this time looking at rotation and then the SU3, SU2 and U1 matrices or operators. I should just say that in this series, at this point, I would have prepared videos on the standard model and then quantum electrodynamics and quantum chromodynamics. But in fact, I've already prepared those videos. They are already in the particle physics playlist. So if you want to see a logical sequence at this point, if you haven't already done so, you should look at the videos, the links to which are on the screen. But assuming that you've done that, then let me just remind you that at the end of the last video in this series, we showed that the commutator of the angular momentum in the x direction with that in the y direction was equal to I h bar Lz, and that the commutator of the spin in the x direction with that h bar, and that's called the spin 1 state. And you'll notice that once again the states are h bar apart. And then I'll just show you another state, which is the s equals 3/2 state. This is for composite particles that we'll meet a bit later on. And here we've got a possible 3/2 h bar, half h bar, minus a half h bar, and minus 3/2 h bar. And once again, you'll notice that each of those are h bar apart, but there are now 4 states. And you will also to notice that the number of states is given by the value of s, 2 times the value of s plus 1. So in this case, s is 0, so 2s plus 1 is 1, there's 1 state. Here the value of s is a half, 2s is 1 plus 1 is 2, there's 2 states. Here 2s plus 1 is 3, there's 3 states. We know what spin is, the Earth spins on its own axis, so that gives us a picture of spin. But we're talking quantum mechanics here, so we need to be very careful that these analogies with the classical world, or the real world that we inhabit, only take us so far. And we have to recognise that angular momentum and spin, when applied to quantum particles, are different to what we observe in the real world. So let's think about some particles and what's called the spin states. There is a spin equals 0 particle. That's, for example, the Higgs boson is a spin 0. That means there is only one spin state. It can't move from any state to any other because there is only one possible state for it to be in. Then there are the fermions, like electrons and quarks, and that is called the s equals 1/2 state. And what that means is that the spin can be either a half h bar or minus a half h bar. There are two possible states. We have labelled this up and this down. So when you measure spin, you only ever get one of two results. You either measure up or down. They are officially half h bar and minus half h bar. Why? Because the difference between the two is h bar. And we showed in quantum mechanics concepts that angular momentum and spin do not come in continuously variable amounts. They always increase by a quantized amount of h bar. So if you want to change from one angular momentum or spin state to another, you have to do it in units of h bar. It's quantized. So when spin changes, it moves in units of h bar from minus a half to plus a half, or from plus a half to minus a half. And those are the only two options for fermions. But bosons, like for example photons, they have three states: plus 1 h bar, 0, and minus 1 in the y direction was equal to IH bar SZ. And we also showed that you could produce similar commutators of y with z and z with x. And in each case, the one that doesn't appear in the commutator is the one that does appear on the right-hand side. And essentially, a key point of what this means is that you cannot measure the angular momentum along the x and the y coordinates at the same time because the commutator does not equal 0. All of this comes out of the material that we developed in quantum mechanics concepts. And similarly, you can't measure spin along 2 axes, or indeed 3 axes, at the same time. You can only ever measure angular momentum and spin along one axis. Now I pause at this point just to point out that we are talking about angular momentum and spin, and of course we can very easily fall into a trap here of saying, yes, we know what angular momentum is. That's kind of when the Earth goes around the Sun. That's got angular momentum.